All right, let's see, this is recording and we're at the right place. So I believe this is where we left off on Monday, because today is totally Wednesday. Where we had figured out the complex power absorbed by our composite load, so lumping load 1 and 2 together to treat it as a single load. And so the next thing that we're going to need to figure out is the complex power that's absorbed by our transmission line, represented by the 0.05 plus J 0.2 ohm distance, which it looks like I forgot a plus sign here. So in order to determine the complex power absorbed by that transmission line, we need to know one of two things: either the voltage drop across the transmission line or the current flowing through the transmission line. Anybody have any thoughts? So, to be clear, what I am referring to is this. I'm going to call this IW for the drop across the wire, or, sorry, and this should be an RMS phasor quantity. So IW for the current flowing through the wire, VW for the voltage drop across the wire. No. Anybody have any thoughts on how we can determine either of those quantities?
We would find the current through each of the loads by interval first finally.
Right.
There's the voltage drop and their complex power, and that current series with this.
Exactly right. So we don't have enough information to determine the voltage VW because we don't know what our source voltage is. That information wasn't given, right? So Ian's suggestion is that all of this RMS phasor current, IW, flows into the composite load formed by lumping loads 1 and 2 together, which we already found the complex power over. So from that, we can say that since S load will be, by definition, V load times IW conjugate, because that's the current flowing into the combined load, we could rearrange this and say that IW is S load divided by V load, right? So the algebraic steps that I'm taking here are I'm doing the complex conjugate of both sides of the equation. So that's going to put a conjugate here and a conjugate here and get rid of this conjugation here. And then I simply solve for the quantity IW. So in this case, that is going to look like 34.335 angle negative 26.227 degrees kilovolt amperes, where the change in sign from S load here to S load here is because I'm doing the complex conjugate operation. And then I'm going to divide it by the voltage drop seen across my combined load, 240 angle, just for the sake of argument, negative 0 degrees volts RMS. The reason why I made a point to put the negative sign here on the 0, even though it actually doesn't do anything, is to remind you guys that when we take the complex conjugate of a fraction, it involves the conjugate of the numerator divided by the conjugate of the denominator, because that's a very common place I see students make mistakes. So Evaluating this, we find that our current I wire is 143.061, angle negative 26. If my stylus will write, there we go, 26.227 degrees amps RMS. And from this, the complex power absorbed by my wire, SW, can be written as the magnitude of I wire squared times the impedance of our wire, which is going to look like 143.061 amps RMS quantity squared multiplied by my impedance of 0.05 plus J 0.2 ohms, which gives me 4.219 angle 75.964 degrees kilovolt amperes. So let me ask you guys a question. Our ultimate goal in this problem, let's review up here, is to determine the value of C that will make the source supply power at a power factor of 0.95 lagging. And we reviewed our power factor correction equation and found out that we knew very, very little about what the pieces that needed to go into that equation were. Okay. So what I am going to suggest here should, I hope, make a lot of sense. If we were able to determine the complex power that was supplied by the source prior to power factor correction, that's going to let us determine the quantity P old and theta old that we need, right? Well, I would argue that the complex power that's being supplied by the source is the same as the sum of the complex powers being absorbed by these two composite loads and our transmission. Right? Effectively, power supplied in the system has to equal the power absorbed in the system. So the complex power supplied by our voltage source, call this SDS supplied, is simply the quantity SW plus S load, which I get to be 37.201 angle 31.192 degrees kilovolt amperes. And since I need P old, I'm going to take the time to go ahead and express this in rectangular coordinates because that's going to give me the quantity P old that I need. Right? So this would be 31.823 plus J 19.267 kilovolt amperes, where this guy measured in watts is the quantity P old that we were trying to find. Everybody okay with that? We can also go ahead and find theta old. Blue. So theta old is going to be the inverse cosine of 31.192 degrees. Which doesn't look like I have written down anywhere, so let me figure out where I put my two calculators. No, not the inverse cosine, just the regular cosine, sorry. Oh, yeah, actually, yeah. Yeah, so I already have theta old. Theta, that's probably why I didn't have it written down. I already had it. Okay, sorry for having a brain fart there. Okay. So we know T old, we know theta old. Let's go back real quick and see, not too far, what other pieces of information that we need. We have this guy, and we have this guy, so we need theta nu. That should be pretty easy to figure out. We still need VRMS as well. So we are in a good situation to determine what that quantity VRMS is. Since we found the power that's being supplied by our voltage source, the complex power that's being supplied by our voltage source, and we know the amount of current that's leaving the positive polarity terminal, it should be very easy for us to figure out what the quantity Vs is, right? So we know that Vs supplied is Vs times IW conjugate, which means the voltage Vs that we're looking for is simply S Vs supplied divided by IW conjugate, or 37.201 angle 31.192 degrees kVA divided by 143, looking at the wrong thing on my screen here, 0.061 angle positive 26.227 degrees amps RMS, giving me a source voltage of 260.037 angle positive 4.965 degrees volts RMS. And this quantity right here is the magnitude of the voltage drop over our capacitor, which we need for our capacitor equation, capacitor determination. So the only thing that we have left to do is figure out what theta nu is. How do we do that? Exactly right. Arc cosine of our new power factor that we're trying to hit. So theta nu will be the inverse cosine of 0.95. Since we're aiming to hit a lagging power factor still, right? We're just increasing it from whatever value the power factor had, which we didn't bother to determine, but that's okay, up to 0.95. We should have a positive sign in front of this arc cosine because we want it to return a positive angle. So the inverse cosine of 0.95 is 18.195 degrees. And finally, then, we know that C is P old times the tangent of theta old minus the tangent of theta new. Let me just double check that. Yeah, old minus new. Divided by omega, which is going to be 2 pi times our linear frequency, which we know, multiplied by the magnitude of Vs quantity squared. If we put in our numbers here, we get an answer of 345.479 microfarads. So this was a fairly involved power factor correction problem. Something like this seems appropriate for your homework, probably less so for your exam unless you want it to be the only question in the test. Caleb, are you raising your hand or are you just playing with your pen? Okay. So any questions on this power factor correction stuff? Should hopefully, Justin, what's up? No. So if you have a time domain signal, dividing by the square root of 2 gives you the RMS phasor magnitude. Okay. But we've worked this entire problem using RMS phasor quantities. So if the units of our voltage is already in volts RMS, that tells us we don't need to fix anything. Does that make sense? So if we scroll up here, oops, slightly too far, power factor in general is defined as the ratio of the average power to the apparent power, which is the exact same thing as the cosine of the power factor angle. So if I know the power factor and I want the angle, I do the inverse cosine of the power factor. Bradley. Shit, sorry. Brain totally far. Branding, oops, sorry. Okay, so that's a great question. So to hit a power factor of unity would require a larger capacitor value, which may require a physically larger capacitor. So it's all about the cost. Most of the decisions that are going to be made in industry regarding power factor correction and all that kind of stuff are all related to cost. How can you do it as efficiently but cheaply as possible? Because that begs the question, why wouldn't you shoot for whatever the threshold is, but leading? Because that gives you the most wiggle room. Well, that requires the most expensive capacitor because it's physically so much larger. Does that make sense? Yeah. Sorry for screwing up your name after knowing you for the better part of 6 months. All right, any other questions? Okay, so what we're going to do now is move on to a topic that is going to seem wildly unrelated to what we've been doing. And to some extent it is. So that's the first page. We are going to introduce the concept of filter circuits today. I'm going to ask you guys a very generic question. What does a filter do? So don't even think about like electrical circuits. So you have a vehicle, or some of you have vehicles. That vehicle has probably an air filter, probably an oil filter. What do those things do? Yeah, pretty much. It gets rid of unwanted stuff. All right. Well, an electrical circuit filter does the exact same thing. It eliminates portions of your signal that occur at unwanted frequencies. Okay. So for example, you guys can probably hear the lights and stuff in this class humming a little bit, right? So if you were making an audio system and you were trying to record something in this class, you would probably want a filter that would reject all frequencies below whatever that is and only pass things that are higher, so that it would eliminate that acoustical noise. In a radio or something like that, probably have a filter system that eliminates the 60 hertz noise on your signal that's being generated by your DC power supply and all that kind of stuff, so that you can isolate your frequencies of interest, all that kind of good stuff, right? So for our introduction to filter circuits, I want to talk about something that probably seems obvious, but might need refreshing, okay? The impedance of an inductor is a frequency-dependent quantity, because it depends on our frequency of operation, omega, right? And I'm going to get to capacitors in a second. Yeah. Oh, wait. Yeah. So, oh my gosh, my head is just so far up my butt today. Thank you, Ian. See what you mean. Okay. Sorry. So for an inductor, we see at very low frequencies that our inductor looks like a short circuit, and for very high frequencies, since there's a proportional relationship between omega and the impedance, at very high frequencies, inductors start to look like open circuits. Okay. For capacitors, we also have a frequency-dependent relationship. But now there's an inverse proportionality, right? So at very low frequencies, the capacitor looks like an open circuit, and at very high frequencies, the capacitor looks like a short circuit. Well, we can design circuits which will eliminate unwanted portions of the frequency spectrum just by effectively taking voltage drops over these frequency-dependent impedances, okay? But before we get to doing that, I want to talk about the different types of filters that we will encounter in this class. And we're going to start with the concept of an ideal filter. So ideal filters eliminate unwanted frequencies while causing no other perturbations or changes in the system, all right? So the first one that we're going to look at, this is going to be our magnitude plot as a function of angular frequency omega. Our first filter has a response that looks like this. Okay. So our amplitude will have its maximum value so that everything gets passed through until we reach what's called our corner frequency, omega c, okay? So everything between 0 and omega c is known as our pass band. And everything between omega c and infinity is what's known as our stop band. Right? So since we are passing frequencies lower than omega C, this is a low pass filter. Low pass filters can be made with first order circuits. So that's RC circuits or RL circuits. We can also make them with higher order circuits as well, but we can make them with as low of an order as one. So a single energy storage element. Okay. The opposite of our low pass filter is the high pass filter. So an ideal high pass filter has this response, where everything above omega C is our pass band and everything below omega C is our stop band. High pass filters can also be made with first order circuits. Next, we're going to introduce the band pass filter. So band pass filters are interesting because they're a combination of low pass and high pass filters effectively. So they're going to have two corner frequencies, omega C1 or omega low, omega C2 also known as omega high, and then a center frequency, omega C, or more commonly, omega naught. So for our band pass filter, ideal, it's going to have a response like this, where all frequencies between our corner frequencies constitute our pass band, and all frequencies outside of our pass band are our stop band. For a band pass filter, we require at a minimum a second order circuit. We need two uncoupled energy storage elements to achieve a response similar to this. And then our final type of filter that we're going to talk about in this class is the band stop or notch filter. So we're going to have a low frequency corner, a high frequency corner, a center frequency, and we're going to have this response, where everything between omega C1 and omega C2 is our stop band, and everything below omega C1 and above omega C2 are our pass bands. Um, So these are what an ideal filter would look like. But it should be fairly obvious that ideal filters cannot be achieved. Okay? For a practical filter, what we're going to see for our responses is something that looks like this. I'm just going to superimpose these on top. All right. If I can draw this correctly. Something that looks like this. Something that looks like this. Something that looks like this. And then something that looks like this. So the higher the order of the filter that we use makes this transition from stop to passband or passband to stop band steeper. So we're getting more and more close to an ideal response at the cost of complexity. Okay. So in this class, we're only going to concern ourselves with first order filters and second order filters. When you guys get to circuits 3 in the fall, we'll start talking about things like Butterworth filters and Chebyshev filters and all that kind of good stuff. Those are really just third order and higher versions of the things that we're going to be talking about in this class, using a special kind of repeated ladder network to increase the order of the filter. Okay, so all filters are based on these 4 simple things, and then we're going to talk about how to implement them in the simplest possible configurations, so that once you learn more circuit analysis techniques and a little bit more math, making sense of why the Butterworth and Chebyshev filters behave like the way they do will make a lot more sense. So for a practical filter, instead of the brick wall response that we see for ideal filters, we get that smoothed over response curve, and that response curve is dictated by what's called the transfer function of the system. So if I have a generic linear filter network, where my options for input signals are an AC voltage that has multiple frequency components. So I'm just going to call this phasor voltage Vn for right now, because we're going to do things generically. Or some frequency dependent current In on the output, I'm going to have some frequency dependent voltage V out, or some frequency dependent current I out. And how our circuit operates on these inputs to generate our outputs is what's called the transfer function, which we're going to call H of omega. In this class, we're specifically going to be looking at voltage transfer functions. Okay. So we can say that H of omega, for the purposes of this class, is simply the ratio of the output voltage as a function of frequency divided by the input voltage as a function of frequency, which is nothing more than a frequency dependent gain, like we saw in our op-amp circuits. All that kind of good stuff. Okay. So let's look at a practical filter circuit. Let's say that I have some resistance R and some impedance 1 over j omega c. And the left-hand side of my circuit is where my frequency-dependent input voltage will be applied. And the right-hand side of my circuit is where my frequency-dependent output voltage will be measured. This, by definition, is a filter of some type. Okay. So I want to walk you guys through the overly complicated steps of determining the transfer function here. Okay. Using voltage division, we can see that V out is Vn times 1 over j omega c divided by R plus 1 over j omega c. And from this, our transfer function h of omega is simply 1 over j omega c divided by R plus 1 over j omega c. That's literally all it takes. All of the filter circuits that we're going to analyze in this class can be treated as simple voltage dividers, where the thing in the numerator is just the element or elements we're taking the voltage drop over. Now, traditionally, we don't leave fractions all over the place because that's going to get weird. So if we multiplied through by a common factor of j omega c divided by j omega c, we could express this as 1 over 1 plus j omega RC. So our transfer function here is in and of itself a complex number. The complex number has both a magnitude and a phase angle. Both of those quantities are dependent on the quantity omega. So what we're going to talk about now is determining what's called the magnitude response. So that tells you effectively which frequencies wind up getting filtered out, as well as the phase response, which tells you how much of a time shift your signals experience as they're being filtered. Okay. So our magnitude response is literally just the magnitude of our transfer function. So how can I get the magnitude of this guy? So the process that I'm going to take, let me detail it right here, and I'll do it in blue over to the side. So for an arbitrary complex number A, which has a real component, lowercase a, and an imaginary component, b. The magnitude of a is simply the square root of the real part squared plus the imaginary part squared. Everybody remember that from circuits 1 or probably your pre-calculus classes and stuff like that as well. The phase angle of A, so if I were to express this as magnitude of A angle theta A as a polar form complex number, the phase angle theta A is the inverse tangent of the imaginary part divided by the real part. Well, this exactly tells us how to get our magnitude response. And this exactly tells us how to get our phase response as a function of omega. So in order to get my magnitude response, I need to be able to split my transfer function into its real part and its imaginary part. Anybody remember how to do that? So what I'm asking you is, how do I take this complex number, which has a rectangular form complex number in the denominator, and make it a rectangular form complex number in the numerator? Math out the reciprocal. Okay, I'm not entirely sure what you mean by that, but we'll do something that involves reciprocals maybe. Okay. Here?
Yes, we want from left to right.
The R is right here. So I multiplied through by j omega c over j omega c, right? So when I multiply this guy by j omega c, I get the 1. When I multiply this guy by j omega c, I get j omega rc.
Okay, it kind of look like the way you were able to divide it all around.
I put the ones on the left hand side because that's just what I do. But yeah. All right, so what I'm going to do here is I'm going to take my complex number 1 over 1 plus j omega rc, and I'm going to multiply this by 1, but a very special one that is the complex conjugate of the denominator over the complex conjugate of the denominator. So 1 minus j omega rc over 1 minus j omega rc. So if we FOIL this thing out here, we're gonna, let's do the denominator first, which will probably make it super obvious as to why I'm doing this. We're gonna have 1 times 1, so that's 1. Then we're gonna have 1 times negative j omega rc, so negative j omega rc. Then we're gonna have positive j omega rc times positive 1, so plus j omega rc. And then finally, we're going to have j omega rc times negative j omega rc, which is negative j squared omega rc quantity squared. Well, what's negative j squared? Positive 1, right? So this is going to look like plus omega rc quantity squared. Obviously, these two terms cancel each other out. And we have 1 minus j omega rc here. And what I'm going to do now is just split this into a rectangular form complex number where I have a fraction that is a real part and a fraction that is the imaginary part, right? So effectively, I'm just going to distribute this denominator to the real side and the imaginary side of the equation. And so that's going to give me 1 over 1 plus omega RC quantity squared minus J times omega RC over that exact same denominator, 1 plus omega RC quantity squared. So I now have split my transfer function into a rectangular form complex number with a well-defined real part and a well-defined imaginary part. That's how it's done. Okay. So technically, none of that was actually the magnitude. It was just making our complex number look like a rectangular form complex number. Now let's do the magnitude bit. So for our magnitude, and just in case I forget to do this, I might also write this as simply h of omega without a bar over it, meaning the same thing as the magnitude. Okay. This is going to be the square root of 1 over 1 plus omega RC quantity squared, this whole thing squared, plus omega RC over 1 plus omega RC quantity squared, this whole thing squared. And from this, I get 1 squared, which is 1, plus omega RC quantity squared divided by 1 plus omega RC squared, this whole thing squared in my denominator. And obviously then I can factor out a common factor, leaving me with 1 over the square root of 1 plus omega RC quantity squared. So this is what my actual magnitude response is, okay? There are no J's or anything in it, which there obviously shouldn't be any imaginary operators in the magnitude here. This lets me plot what this filter circuit is doing as a function of omega, right? We can do a quick and dirty guesstimate as to how this guy behaves by looking at h when omega is equal to 0 and looking at h when omega is equal to infinity, okay? So what does this guy simplify to at omega is equal to 0? 1, absolutely right. That means at very low frequencies, signals are getting passed. What does this guy simplify to when omega is equal to infinity? 0. Which means at high frequencies, all of our signals are getting rejected. So what kind of filter is this? It's a low pass filter, right? Low frequencies are getting passed, high frequencies are getting rejected or attenuated. So this is a low pass filter. All right. While we are at it, we can determine our corner frequency, okay? So corner frequency in a filter circuit is defined to be the frequency at which the signal loses half of its power, okay? So for all frequencies below omega c, we're operating at something above half power. And for all frequencies, all frequencies below omega c, we have above half power, and all frequencies beyond omega c, we're operating at below half power, okay? Power is related to the voltage squared. Since we are looking at this transfer function in terms of input and output voltages, that half power corresponds to a reduction in magnitude of 1 divided by the square root of 2, right? Because if we squared the voltage, 1 over square root of 2 times 1 over square root of 2 would give us half power, okay? So at what frequency? So let's see, omega c is defined as the frequency at which h of omega, the magnitude, is equal to 1 over the square root of 2. So for this particular circuit, what should that be? Exactly right, 1 over RC. So effectively, we want this quantity to equal 1 over square root of 2, which means we want the denominator to equal the square root of 2. Or everything inside the radical to equal to 2, which means we want this part over here to look like 1, which is only true when omega is 1 over RC. Surprise, surprise. Our first order circuit depends on the time constant yet again. Who would have thunk it? Yeah. When we have our second order circuits, that center frequency omega naught is literally the same thing as our center frequency or our omega naught for our RLC circuits. It's the frequency at which the impedance becomes purely real. But anyway. So we know that we have a low pass filter. We know what the corner frequency is. The only thing left to figure out about this particular circuit is its phase response, or how the phase of the signal changes as it gets filtered. So our phase response, theta h of omega, is simply the arctangent of the imaginary part, which is negative omega RC divided by 1 plus omega RC quantity squared, all divided by the real part, which is 1 over 1 plus omega RC squared. So we have the division of two fractions, and they have the same denominators. So those guys are going to cancel each other out. And so this leaves us with the arctangent of negative omega RC, which is the same as negative arctangent of positive omega RC. So if we were to plot this, the magnitude and the phase response, it would look something like this. Here's omega, here's the magnitude, H of omega. We're going to have pass a maximum of all of our signal for low frequencies. Let's see, this is 0. Let's throw this as omega C. Something like this, where I know this doesn't quite, let me try to redraw this a little bit better. Don't know that that helped. So what's supposed to be happening is that right here would correspond to 1 over root 2, but I'm not drawing the scale correctly. And over here will be our phase response. Where up here will correspond to positive 90 degrees. And down here will correspond to negative 90 degrees. And it should look something like this. Let's see. So we got 15 minutes left. Let's do a simulation. All right, so for our circuit, we had something simple, right? We had a resistor in series with a capacitor, and the resistor was oriented like this. Our capacitor was oriented like this. And I don't really have to do this part here, but I'm going to just for the sake of argument. I'm going to put ground down here. And then I'm going to throw a voltage source over here on the left. Connect that up. And then I am going to label that node on the top right as V out. And just for the sake of argument, we'll call this guy V in. Okay. So before we start worrying about our source, somebody give me a value for my resistor. 12. Okay. Just 12 ohms. All right. What about my capacitor? 1 millifarad. 1 M. Okay. So to get my source set up correctly, I'm going to go to advanced. And I'm going to leave the entire left side the hell alone. What I'm going to play with is right here where it says small signal AC analysis. Okay. I'm going to make the AC amplitude 1 volt. So that when I plot my output voltage, it is my frequency response, right? Because V out divided by an input voltage of 1 volt over all frequencies gives me my transfer function, okay? I'm going to leave the phase. So I'm just going to start it at a frequency of 0 and just let it do whatever it needs to do. And I'm going to edit my simulation command, and I'm going to go here to AC analysis. All right. Where I get to tell it this type of sweep. So it should be octave, decade, linear. I'm just going to do it decade. The number of points per decade, let's say 1,000. Let's make my start frequency 1 millihertz and my stop frequency 1 megahertz. And I'll probably wind up changing these once I see what things look like. Okay, so I'm starting.
It's going logarithmically.
Pardon?
That guy means going logarithmically.
Yes.
You like 1,000 points from one end to one, or 10 end.
So from 10 to the -3 to 10 to the -2 should be 1,000 points, 10 to the -2 to 10 to the -1, another 1,000 points, etc. Let's see what happens here. Drop this on the bottom. And then run my simulation. And like I said, if I just click this output voltage node, this should give me my transfer function. Okay. Let me move this out of the way here. Okay. So LT Spice gives us our plots where the units of decibels are on the left-hand side. A decibel is 20 log the value of the transfer function at that frequency. Okay, so it's 20 log V out over Vn effectively. All right. So when we hit -3 decibels, that is our half power or corner frequency. I'll probably make you guys prove that in a homework assignment. But 3 decibels corresponds to when our signal has decayed down to 1 over the square root of 2 here, where 0 dB is 1, which is our maximum value. Okay. So if I click here, I should get traces, right? I can see. I'm going to move this guy over, and I'm just going to try to move it to a point where the magnitude is -3 decibels. Slightly too far. All righty. So I get at a frequency of 13.24844 hertz. This is our corner frequency. So what is 1 over R times C in this case? So 1 over 12 times 1 times 10 to the -3. 250 over 3, or 83.333. So why isn't this number 83.333?
The new frequency are 83 should be angular.
Exactly right. Omega that we determined is an angular frequency, which should be exactly 2 pi times larger than this value. So if we multiply, or we divide that 83.333 by 2 pi, we get 13.263, which is pretty dang close. All right. The solid line represents the magnitude plot. The dashed line represents our phase plot. We're only including positive frequencies, which is why we only see the positive half of our phase plot, whereas the plot that I gave you included the negative frequency bit as well. Okay. So expect to be playing around with graphs like these an awful lot for the next couple of days in this class, and then a whole hell of a lot in your later classes. Jared. Okay, so when I clicked on this, like I left click on the signal that I'm looking at, that pulls up my trace plot. So just to show you, I've deleted it, I'm mousing over it, I left click, it shows up.
It's like a graph of how practical filter like how the graph of the dampening the voltage.
Exactly right. So we can see that up until a frequency of somewhere between 1 and 2 hertz, literally all of the input signal is getting passed. At around this point, we start to see a small reduction. And as we increase in frequency, more and more of our signal is getting attenuated, right? So for every 20 decibels of decay, that means our signal power is being reduced by a factor of, I think it's 1,000. It's either 10 or, excuse me, it's either 10 or 100. I can't remember what's on there. Maybe it's on. Should be able to figure that out. So the signal power every 10 decibels is a factor of 10. Yeah. So when we're here, our signal power is reduced by 10. When we're here, our signal power has been reduced by 100, 1,000, 10,000, etc. So 60 dB is generally accepted to be the largest reliable attenuation that we can get. And I say that because that means that we've attenuated the signal power by a factor of 1,000,000. And that's usually somewhere around the maximum resolution of our measurement, what our measurement device can reliably do. Is measuring 1,000 or excuse me, 1,000,000-fold difference between our input signal and our output signal. It still continues to decay linearly on this logarithmic plot beyond that point, but 60 dBs worth of attenuation is the maximum that if we're using a measurement instrument, we can really have any reliability. All right, so when we resume on Friday, we'll start to look at second order filter circuits. Technically, there are still 3 more first order filter circuits that we could look at. So we could swap R and C to observe that we get a high pass filter. And then we can do RL circuits and find out that we get a low pass filter and a high pass filter. I'll probably make you do that for your homework. It's a waste of time in here. We'll get to second order circuits like band pass and band stop filters on Friday. Yeah, so you guys, what